En Conciencias contribuimos al fortalecimiento de las entidades del Sistema Nacional de Ciencia, Tecnología e Innovación a través de apoyos directos.
A nosotros, desde que nos formamos, Conciencias nos ha apoyado en ingeniería de tejidos y en el desarrollo de soportes, y nosotros somos un grupo que se conoce porque trabaja en colágeno. Sin ese apoyo anterior de Conciencias, no habría sido posible que nosotros estuviéramos haciendo las evaluaciones que estamos haciendo.
Apoyamos la transformación social y económica del país, estimulando la generación de conocimiento mediante iniciativas científicas o tecnológicas. Identificamos y hacemos visible la labor de los científicos y los grupos de investigación.
Conciencias creo que ha hecho unas cosas muy importantes. Primero, pues hacer la convocatoria y financiar estos proyectos, pero la importancia que tiene es que cambió a través de estas convocatorias esos esquemas que había antes, que eran muy puntuales y muy proyectos por unos términos muy definidos, a decir, miren, esto hay que pensarlo a largo plazo para que volver los programas de investigación articulando diferentes proyectos en un mismo programa.
Financiamos becas para la formación del capital humano que requiere el Sistema Nacional de Ciencia, Tecnología e Innovación en los niveles de maestría, doctorados nacionales y en el exterior. Ofrecemos apoyo a las poblaciones vulnerables para la creación de empresas solidarias. Contribuimos al mejoramiento de la calidad de vida de las comunidades en condiciones de pobreza a partir de la implementación de soluciones científico-tecnológicas.
El vínculo que hay con la comunidad pues se da mediante una convocatoria que abre pues, Conciencias mediante pues, ideas para el cambio. Pues, gracias pues, a nuestro Dios, la Gran Vía fue beneficiada pues, para este proyecto, el cual es el abastecimiento de agua potable para toda la comunidad, pues que sin duda alguna pues, generaría mejorar la calidad de vida de todos esos niños y las personas pues, que habitan en esa comunidad tan vulnerable.
Fortalecemos las capacidades de gestión de innovación en las empresas y organizaciones colombianas. Nuestra carta de navegación es el plan anual de convocatorias que tiene como objetivo promover la generación, aplicación y uso de conocimiento en ciencia, tecnología e innovación de cada uno de los actores del sistema: estudiantes, científicos, investigadores, docentes y empresarios. De esta manera, Conciencias apoya el desarrollo de soluciones científicas, tecnológicas e innovadoras a las necesidades de la comunidad colombiana. La locomotora de la innovación potencia la prosperidad de Colombia.
Here to Medellin, we're really happy that you have all made it. This is the 10th version of the Silafae, and it's the second time it takes place in Colombia. It is really very satisfactory to see the increase in the high energy physics community in Colombia and the widespread participation of all other Latin American countries in this 10th version of the Silafae, and especially also to all those speakers that are coming from other countries. We are really happy that you have come here. Of course, the most important part is the scientific component of this event, and we think the program really offers a nice breadth and depth of subjects. I'd like to thank all of the speakers and all of the poster presentations for their contribution that is really going to allow us to have a very successful Silafae. In addition, I would like to express a strong appreciation to all of the members of the local organizing committee that have really worked very hard for this event to happen and to make it a success, and to all of the 8 institutions that have formally backed the Silafae, and some of our sponsors that include the Colombian Physics Society, UTN, which is where we are located right now, the city of Medellin, and of course Conciencias. We really hope that you all have an enjoyable conference, that you can enjoy Colombia and Colombian hospitality. And really now we should start with what we really are all very much interested, which is the physics. So I hope it will be really, really the best Silafae ever. Thanks again.
Good morning to everyone. Let us start the morning session. The opening talk is going to be delivered by Professor Silafae. Professor, thank you for being with us again.
Okay, mucho gusto. Okay, so it's a great pleasure to be back in Medellin. Just a small year since I was here last time. And thank you very much for the kind invitation to give a sort of opening talk, which I would like to classify as a sort of personal outlook about where we are and where we're going. So I like to start these talks with this image that you see here, which I think sort of summarizes where we are. We have, as a community, made a major discovery a couple of years ago, and of course I'm going to be devoting some time to discussing the implications of that discovery. But of course we all hope that in addition there are other things on the horizon that maybe we will soon get close to. So there's going to be many more specialized talks during the course of this meeting. And you should regard my talk as being a sort of hors d'oeuvre before the main courses. But I would like to spend a little bit of time discussing what the discovery of the Higgs boson may be telling us, what else there may be, and how else we may hope to find it, themes that, of course, will be recurring during the course of the meeting. So this picture was actually taken in 1965, shortly after Peter Higgs proposed the existence of the Higgs boson, and he's actually working out, I guess, some of the details of his theory here. I'm not sure whether the resolution on the screen is sufficient for you to figure out his scientific secrets. So the first run of the LHC has been a fantastic success for the Standard Model. So many cross-sections have been measured, and as you can see from this picture, generally they're all in good agreement with the Standard Model predictions. This includes QCD, it includes production of vector bosons with jets, it includes production of top quarks, and of course it also includes the production of the Higgs boson. So as I and other speakers will be discussing in more detail, the Higgs boson has been observed, produced in various different channels, and again you see that grosso modo the predictions agree with the data. This one down here, where if you've got a very sharp eye you might see a 2 sigma discrepancy, don't take that terribly seriously. That's TT bar plus Higgs, an interesting physics topic which I'll come back to later on. So, unfortunately, I understand that Frank Petrello is not able to come, so I just put in a couple of slides about QCD for many reasons. One, which I've already written here, that this is the basis for pretty much everything at the at the LHC. Right? The dominant production cross-sections are strong production cross-sections, and you have to understand QCD, be able to calculate accurately if you want to make accurate predictions. So you can make tests of the Standard Model predictions, and among those that I'm going to discuss in this talk are top physics, particularly the mass of the top quark, production of new particles, of course, principally the Higgs boson. If one understands QCD better, one can hope to dig out additional signals for new physics, for example, looking for boosted jets and dissecting their structure. And of course, apart from all these exciting things, there is also the routine business of understanding better the backgrounds that may potentially pollute the signals that you might be more interested in. So as I said, QCD works fantastically well for predicting production cross-sections at the LHC. Here I've got a slide which shows the success in predicting the cross-sections for jets. And you can see here we're talking about a dynamic range of a factor of 100 in jet energy and a factor of, not sure how much it is, 10 to the 12 or something like that in terms of cross-section. So what do we learn from this? Well, one of the things that we learn from this is that the strong coupling constant continues to run. And this, I think, is a beautiful plot that was produced by the CMS collaboration, some of whose members are here in the audience, showing that the QCD coupling strength runs out to and maybe even beyond the 1 TeV scale. And the measurements at the LHC, perhaps not yet quite as accurate as the measurements at low energies, but they're certainly very consistent with the picture that have been built up from previous low energy experiments. So one of the topics in QCD that I'd like to discuss a little bit is the mass of the top quark. So in addition to being a very basic parameter of the standard model, as many of you know, the precise value of the top quark mass and the Higgs mass, those values are very important for understanding the stability of the electroweak vacuum. And this is a topic that I'll come back to later on in my talk. So what do we know about the top quark mass? Well, what I show here is the official world experimental average for the top quark mass, which has an uncertainty which is now below 0.5%, which is pretty damned impressive. But one has to be careful, because what is told to you by the experiments is not necessarily what a theorist might understand by the top quark mass. There are various different definitions. There's the running top quark mass, which is a natural quantity if you're a theorist and you're doing some sort of MS bar regularization scheme. There's the pole mass, which perhaps to an experimentalist might appear the most natural one. Where is the physical pole of the particle? But actually what appears in the Monte Carlos is often a different thing, and the precise relationship between that top quark mass and the top quark mass that you as a theorist might find easier to interpret is perhaps not so clear. So there is an uncertainty here at the level at least of a fraction of a GeV. Now, after the publication by the Fermilab and CERN collaborations of this official world average, in fact, new determinations of the top quark mass came out from both CMS and D0 collaborations. And if you compare these with the world average, you see that CMS is pulling down, D0 is pushing up, and we'll come back later to the potential implications of that. Did I just skip over? Yes, I skipped over one. So I also wanted to make a few remarks about Higgs production, because of course that's very important for the interpretation of the Higgs signal. And I'd like to pay tribute to the fantastic amount of work that's been done by many groups around the world calculating Higgs production cross-sections and decay properties to next to next to next to next, well, a lot of nexts leading order in QCD. However, the situation is still not completely satisfactory. And I think there's two problems here. One is actually calculating the higher order perturbative diagrams, but the other one is the Parton distribution functions that enter into the cross-section. And this is a picture that I've stolen from I'm not quite sure where, but it shows you that depending on which Parton distribution function you use, you may get rather different ideas about what the Higgs production cross-section might be. So this is an uncertainty still in the interpretation of the data, and we hope that with run 2, with new determinations of Parton distribution functions from the LHC experiments themselves, that this uncertainty can be reduced at the same time as the theorists do the next to next to next to leading order calculation. So I just put in a couple of slides about flavor physics. So, of course, as we all know, the CKM model works fantastically well, accommodating or predicting CP violation in the K, B plus or minus BS systems. There was a bit of a flurry of interest a couple of years ago when it seemed that there might also be detectable CP violation in the D system. Unfortunately, that's gone away. So unfortunately, yet another victory for the standard model. Of course, one of the most exciting things in the last couple of years has been the observation of the rare decay BS goes to mu plus mu minus, which unfortunately, yet again, seems to be in agreement with the CKM model and the standard model in general. But before one gets too carried away, one should remember that there is potential for substantial BSM contributions elsewhere in B physics. And this, for example, is how much BSM contribution there could be to BS mixing. So I think it's still an open question to what extent any new TeV scale physics really copies slavishly the CKM scenario via minimal flavor violation. So perhaps the second most exciting discovery at the LHC Run 1 was the observation of BS goes to mu plus mu minus decay. And just within the last week or two, the CMS and LHCb collaborations have produced a joint paper where they give us the definitive information on this decay mode, which is now observed with a significance somewhere around 6 standard deviations. So this is a fantastic success, as I already said. However, I would like to underline that there is an issue here, which is the relative strength of BS goes to mu plus mu minus and BD goes to mu plus mu minus. And as you can see from this plot here, taken from the joint paper, if you look at the likelihood function, okay, for BS, everything looks consistent with the standard model. There is a hint that the BD signal may be significantly larger than in the standard model. Whether this turns out to be true or not, of course, we have to wait for run 2. Now, there are other puzzles in CKM physics. For example, one of them is to distinguish all these various different penguins. There's this well-advertised angular distribution anomaly in B goes to K star mu plus mu minus decay. There's still some questions about VUB, whether there is some sort of leakage of the weak interaction strength. And of course, we've got the dimuon asymmetry from the tevatron. So there's plenty of topics still to be discussed and plenty of topics for LHC Run 2. Okay, now I want to come to a somewhat more substantial piece of the hors d'oeuvres, which is Higgs physics. So ATLAS and CMS have now produced the definitive results from LHC Run 1. And of course, the primary quantity of interest is the mass of this particle. So this you measure accurately either via gamma-gamma decays or ZZ star into 4 leptons. These are the determinations from ATLAS. These are determinations from CMS. And if you combine them together, you get a mass which is around 125 GeV. Now, there was a bit of a flurry of interest a year or two back when the mass determinations by ATLAS in the gamma-gamma and 4 lepton channels seemed to be different by a couple of sigma. So some people said, oh, maybe there's 2 particles there. What's amusing is that CMS also finds a small difference between the masses in gamma-gamma and 4 leptons, but the difference has the opposite sign. So you don't need 2 particles, you need 4 particles if you want to accommodate all the data. So the mass of the Higgs boson, like the mass of the top quark, is important not only in itself, but also for the stability of the electroweak vacuum, a topic that, as I said, I'll return to later on. So I said that the mass of this particle was perhaps the most fundamental property. One could argue whether a more fundamental property is the spin of this particle. And we all had a little bit of fun a year or two back devising ways to determine the spin of this particle. And well, this is a plot produced by CMS where they compare the 0 plus hypothesis with many other possible hypotheses for the spin parity of this particle. All these tests are in excellent agreement with the 0 plus hypothesis, and alternative spins, alternative parity assignments seem to be strongly disfavored. So Peter Higgs can afford to smile. Okay, so we know the mass, we know the spin. What about the couplings of this particle to other particles? So here we have a combination that was published by the ELLIS collaboration a few months ago, and putting this all together, they got a mean signal strength for this new particle of 1.30 plus or minus blah, 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 times the standard model prediction. So again, consistent with the standard model. Subsequently, they've in fact come up with some small updates on some of these signal strengths. And so I think that if you did this average today, you get a slightly different value, maybe even a little bit closer to the standard model value. This is the corresponding analysis by CMS. CMS and ELLIS adopt different conventions for their green bands. So, well, actually, maybe they don't. Anyway, the average of CMS is precisely 1.00. So I guess it's ambiguous whether this green band is centered on the standard model prediction or the experimental determination. So it's one thing to say that the predictions of the standard model are consistent with the data. It's something else to ask, well, does this particle actually do what it's supposed to do? So, of course, what it's supposed to do is to couple to other particles proportional to their masses, because after all, this particle is supposed to be the signature of the mass generation mechanism. So exercise that we did last year with my student Tivong Yu was to just parameterize the couplings, not as relative to the standard model, but as some power of the particle mass. Of course, with the standard model, the power of the coupling to fermions should be 1, the power of the coupling to bosons should be 2, but maybe they differ by some power, fractional power epsilon, and maybe the overall scale of the coupling is different from the standard model value. The standard model value, of course, would be 246 GeV. And so this plot shows you that, first of all, the couplings do seem to be essentially proportional to the mass. The power here is incredibly close to 1, okay? So, and the overall magnitude here, 244 GeV, is very close to the standard model prediction. So again, Peter Higgs can afford to smile. So on that plot, you had gathered together the information about the Higgs couplings to vector bosons and to fermions. But you could ask yourself whether the couplings to fermions conserve flavor or not. And well, of course, there's upper limits on possible flavor violation coming from low energy tests, indirect upper limits on the possible flavor violating couplings of the Higgs boson. Those actually exclude, at least for the foreseeable future, observable quark flavor violating Higgs decays. However, they do not exclude the possibility of lepton flavor violating Higgs decays. And in fact, when we did this analysis with Blankenberg and Gino Isidori, we found that the branching ratio of the Higgs into tau mu or tau electron could possibly be as large as 10%. So the CMS collaboration recently released an analysis where they tried to establish an upper limit on Higgs into tau mu decay. And obstinately, the branching ratio refused to be 0. Of course, only at the level of 2 sigma, so you shouldn't take this seriously. But as you can see, the data are consistent with a non-zero branching ratio at the level of 1% or so. So that's completely consistent with the upper limits on flavor change and neutral interactions. In itself, this is not significant. We would like to see the corresponding analysis from the ATLAS collaboration, and of course we look forward to seeing what happens at run 2. Now, I mentioned earlier on that TT bar Higgs is something which has not yet been observed at the LHC. I'd just like to advertise the fact that TT bar Higgs, and for that matter, single top plus Higgs, are interesting processes for measurements at LHC run 2. In particular, it's an interesting playground for looking for possible CP violating couplings of the Higgs. I mentioned earlier on the Higgs is at least predominantly a scalar particle, but it could have pseudoscalar couplings, perhaps to some fermions, and this is something which you can probe via TT bar Higgs and single top plus Higgs production. So of course there's constraints on this possibility coming indirectly from the glue-glue Higgs and the Higgs to gamma-gamma couplings, which are shown in this sort of banana plot up here. So the region which is allowed by the data is that banana around there, or boomerang if you prefer. So that boomerang is in the plane of CP even and CP odd couplings. If you vary the ratio of CP odd to CP even, what happens? Well, what happens is that the TT bar Higgs cross-section goes down and the single top plus Higgs cross-section goes up. So we're certainly looking forward to more precise measurements of TT bar Higgs and a search for single top plus Higgs production. And when you do observe these processes, then it would be interesting to look for signatures of CP violation, such as transverse asymmetries. So plenty of physics there for LHC run 2. So, of course, the big issue, to my mind, in Higgs physics is whether this is truly an elementary particle or whether it is actually a composite particle. So here I think one could say that theorists divide themselves into 2 schools of thought. On the left we have the elementary people who expect that probably the Higgs boson is accompanied by supersymmetry. And on the right we have the composite people who, back in the day were predicting the existence of a very heavy scalar particle which would be inconsistent with the data. But of course, as time went along, they became a lot cleverer, and most composite people now would propose some sort of scenario where the Higgs boson is interpreted as a pseudo-Nambu-Goldstone boson of some higher symmetry, which is then broken down at lower energies to the standard model symmetry. So a characteristic of these models is that you would expect a lot of new physics around the scale of the ultraviolet completion of these theories. These theories need an ultraviolet completion because although unlike the supersymmetry where those encapsulations are stabilization was the overall deformation theory, is like the model. That's not the case. The heat is ultraviolet completion or some stable. Form part of that ultraviolet completion. So I expect that Christoph is going to discuss this in more detail in his talk, but one of the major industries in Higgs physics over the last few years has been parametrization of the couplings of this particle, which could serve as an arena for probing possible composite nature. So the idea is that you take the couplings as they are in the standard model, and you rescale them all by factors, which are written here in red, A, B, C, D, and so on. So you normalize so that these factors would be equal to 1 in the standard model, and you look to see what the data are telling you. So this again is this is something which many, many people have done. I'm just going to show you a few images from this paper that I wrote with Tuvong Yu, just to show you how the constraints coming from the different couplings of the Higgs to different particles constrain this overall picture. So this is the information that you get from Higgs to BB bar coupling. So on the horizontal axis here, up, put W, you finish up with this global picture, which actually tells you with a fair degree of confidence that the sign of the Higgs top coupling is as predicted in the standard model. So this bright spot, that's what the data are telling you. Standard model, which is the green star. And you also see that these yellow lines, which correspond to composite models, some of these models don't agree too well with the data, and some of them could agree with the data, but if you adjust the parameters so that they are close to the standard model predictions. So, no evidence here for deviation from the standard model. So more recently, and again I'm sure that you'll hear about this from Christoph, there's another trend amongst the theorists, which is to assume that indeed at the tree level this is a standard model Higgs boson, but that you parameterize new physics by additional dimension 6 operators, well, dimension 6 and beyond. Already dimension 6 is fairly complicated, so I think for the time being people are just focusing on dimension 6 additions. So you construct all the possible dimension 6 operators made up of standard model particles, and then you try to constrain those couplings using precision electroweak data, Higgs data, triple gauge couplings, and so on. So this is an exercise that so far as I'm aware, only theorists have been engaged in. I hope that in the near future, ATLAS and CMS will also do this, perhaps in a more professional way than what we do. Now, the beauty of this framework is that you are able to discuss in a connected way, not just Higgs physics, but also precision electroweak physics, other tests of the standard model, like triple gauge couplings, and so on. So this is taken from a recent paper that I wrote with Tuvong Yu and Veronica Sands, where we looked at the constraints on such operator coefficients that come from precision electroweak data. On the left here you have leptonic observables, on the right you have hadronic observables, mainly from LEP. You also get interesting information from, obviously, Higgs properties, and in particular associated production of the Higgs boson. And I'd like to underline the interest of measuring not just the rates for things like associated production, but also kinematic distributions. The kinematic distributions also contain additional information that can help constrain those high dimensional operators. So this is what we get when we include the information coming from Higgs signal strengths and associated production. And this is the result of a global fit where we include not just associated production, but also LHC measurements of triple gauge couplings. So the black bars here correspond to a global combination of all the relevant coefficients, and the green bars correspond to what would happen if you just set one operator at a time, allowed one operator at a time to be non-zero. So you can see from this that, well, depending on the operator coefficient, you're probing new physics at, TV-ish scales in this way. So far, this is relatively imprecise. I'm sure that LHC Run 2 will offer much greater prospects for doing this sort of analysis, and as I said, I hope that this sort of approach will be taken over by the experimental collaborations. Okay, so far, so bad. Right? So far there is no sign of any discrepancy with the standard model. And so, of course, there's people out there, maybe in the funding agencies, who are saying, well, maybe there's no physics detectable beyond the standard model, so let's just stop doing particle physics and go off and do cosmology, which I'm sure will make Leonardo happy. I'd just like to comment that there's been many instances in the past when distinguished physicists have said that physics is game over. So this is Michelson, 1894, just before the discovery of radioactivity and the electron. The more important fundamental laws and facts of physical science have all been discovered. Not to be outdone, Lord Kelvin, a few years before the discovery of quantum mechanics and the photon, special relativity, and one or two other things. There's nothing new to be discovered in physics. All that remains is more and more precise measurement. Stephen Hawking, 1980, is the end in sight for theoretical physics. But my favourite quotation along these lines will be familiar to many of you who had your grant proposal rejected. So many centuries after the creation, it is unlikely that anyone could find hitherto unknown lands of any value. This is when the Spanish Royal Commission initially rejected Christopher Columbus' grant proposal. I think that this audience here would agree that indeed there were unknown lands. Now, I just want to motivate you that indeed there is physics out there beyond the standard model. I should, by the way, point out that the lady on the right is a nuclear physicist. So I would like to argue that the standard model is not enough. And in honor of James Bond, I give you 7 reasons thinking that the standard model is not enough. So one is that empty space is unstable. Stephen Hawking got into the news a few weeks ago proclaiming this, and I will discuss it in a bit more detail in a moment. Dark matter, the origin of matter, these are things that you cannot explain within the standard model. Masses and machines, the hierarchy problem, again, not explained within the standard model. Cosmological inflation, hearing about that, seems to require physics beyond the standard model. Of course, if you want to make a quantum theory of gravity, you certainly need physics beyond the standard model. So I, of course, have my prejudice as to what that new physics is, and I'll come back to that later on. So let me talk a little bit about this issue of battery stability. So the point here, of course, is that the Higgs self-coupling, like any quantum field theory coupling, is subject to normalization. It normalizes itself, and perhaps more importantly, it is normalized by the top quarter. that top quark renormalization is negative. And if you put in values of the Higgs mass and the top quark mass I discussed earlier on, the Higgs self-coupling would become negative at an energy scale somewhere around 10 to the 11 GeV. When the coupling becomes negative, potential goes negative, and our vacuum becomes unstable. So we like some new physics to stabilize it, which could, of course, be supersymmetry, but there are also other possibilities. So let me discuss this in a little bit more detail. This is obviously a very important argument. So here is the, if you don't have the expression, Mexican hat part of the effective standard potential. You renormalize, you discover that the coupling goes negative, and that means that potential apparently goes to infinitely negative values. So that generates instability, and this paper by Vitazzo et al. Last year, they estimated this instability scale, and if you put in the then central values of MX and then top, you were probably in this actually metastable region. Now, if you put in the current world average that I mentioned earlier on, you get this little green oval here, which perhaps even slightly more significantly is sitting in this unstable region. But as I mentioned, subsequent to the publication of that world average, there have been new determinations of n top from the CS collaboration on the low side, from the G0 collaboration on the high side. So what do those mean for the future of the universe? Well, CMS might say, well, perhaps there's no problem. On the other hand, G0 would say, Houston, you do have a problem. So this, I would regard at the moment as not being proof that our electric vacuum is unstable. It's a fairly solid indication that this is something that needs to be followed up at LHC round 2. I think we probably now know the Higgs mass with sufficient accuracy, but we would like to know better the top quark mass. That means a joint work of the experiments on the one hand, and also the theorists to reduce the uncertainties. So what happens if you go over the hill? So this has been analyzed by various groups over the last year or so. These are some plots taken from the paper by Prof and now. And they analyzed carefully the evolution of the theory through and beyond the barrier. And they gave various possible ways in which you could rescue the situation. But any of these ways requires some sort of new physics. Okay, so what new physics? So historically, the motivation for thinking that there might be additional new physics around the TB scale has come from the hierarchy problem. And there's certainly no shortage of theoretical approaches to alleviating or solving that problem. And this is a roadmap that I took from a talk by Nathaniel Craig at the LHC Physics Conference a few months ago. So which of these approaches should one take? Well, I make no bones about it. I prefer supersymmetry. And my philosophy about supersymmetry is summarized with this cartoon from World War I. So there's a couple of guys in the trenches, they're being bombarded, and one of them says to the other, if you know of a better hole, go to it. So that's a little bit the way that I feel about supersymmetry. So there's a lot of people knocking supersymmetry and saying, I haven't seen supersymmetric particles yet, supersymmetry is a load of scrap and all that. Please, tell me of a better theory of supersymmetry, and then I'll answer. So that's why I write supersymmetry in the largest possible font on my slides, and I would even push back on the critics of supersymmetry by saying LHC11 has given us many additional reasons for liking supersymmetry. It can stabilize the electric vacuum. It made a successful prediction for the mass of the Higgs boson. Simple models predict that the Higgs couplings should be similar to those in the standard model. So as I said, LHC11 has provided, to my mind, many additional motivations for supersymmetry. Too bad I didn't actually find it. And of course, all the traditional motivations from band unification, string theory, dark matter, and so on. Okay, so back to Nathaniel Craig. So this is another map of, in this case, superspace. And it's an unfortunate fact of life that there are no clear signposts in superspace. There's always many possible supersymmetric scenarios. Which of them is actually one realized by nature? Who knows? So what does the poor experimentalist do? Well, poor experimentalists obviously take the simplest model, which is so-called M-super, which I would prefer to call it constrained SSM, where you postulate soft supersymmetry parameters are universal at the input and count scale. And this is a plot from the atlas showing various different constraints, looking for jets mass missing energy, possibly accompanied by leptons, deep quarks, and so on. Many different searches, and they're combined together in this M0, M1 half planes, and this is a supersymmetric fermion boson masses. So this is, as I repeat, in the context of the simplest possible supersymmetric model. So now you can combine these data with other constraints, which is an exercise which I've been doing with the master code collaboration and other groups do similar analyses. And in this plot here, we try to put together the way in which various different constraints interplay. So G-2, remember the anomalous magnetic moment of the muon, that would have preferred smaller values of supersymmetric particle masses than are indicated by the LHC data. LHC is obviously pushing us out this way. There are constraints coming from dark matter, which argue against very large spherical masses. BS goes to mu, that's another instance of a measurement that agrees with the standard model, and therefore some way constraints supersymmetric scenarios. So there's many different pushes and pulls on the supersymmetric parameter space. So what do you finish up with as an allowed value for the Lorino mass, for example, which is many scenarios of primary supersymmetric particle which you would make in the LHC. So what you find is that at the 95% confidence level also, that it would have a mass bigger than about 1.8 TeV. So what are the prospects for discovering this particle in the future, in this particular simplified scenario? Well, LHC at high luminosity and 13 or 14 TeV in the center of mass can explore up to masses between 3 and 4 TeV. So a substantial region of supersymmetric parameter space will be explored, although substantial areas will not be explored. So this is a plot from the Atlas collaboration showing M squawk on the horizontal axis, M Lorino on the vertical axis. And you may remember a couple of slides ago, I had two preferred regions of supersymmetric parameter space, one at relatively low masses, one at relatively high masses. This red line here shows you the LHC search sensitivity. The lines for exclusion, the lines for exclusion at 300 femtobarns and discovery at 3000 femtobarns more or less coincide. What they show you is that in these simplified models, you will cover the low mass region with the LHC. Now what happens if you choose a less constrained model? So there's interest in so-called phenomenological MSSM, where you allow the soft supersymmetry breaking parameters to float. But in that case, the mass limits get weaker, and also the LHC sensitivity is also somewhat reduced. That's what's shown on this slide here. So here the black lines correspond to the lower limits on supersymmetric particles of LHC 1 in more general PMSSM. And you see, for example, now that we know that these light on TV. And this shows you the expected reach with the LHC in the future, which goes up this time perhaps to somewhat less than 3 TeV in this more general scenario. So, conclusion, these more complicated models is actually rather similar to those in the simple models, namely that there is significant parameter space that will be explored by the LHC, but perhaps not all of it. I'd just like to mention one feature of these more general supersymmetric models, which is that unlike those constrained models, they could potentially reconcile the absence of supersymmetry that they see with the enormous magnetic boundary result. As I mentioned earlier on, there is tension between the LHC and measurement of G-2. That tension is potentially reduced in the more general supersymmetric models. It's great news that both in the US and in Japan there are experiments planned to measure G-2 greater accuracy in the future, so that we can pin down whether or not this discrepancy with the standard model is real or not. So, I'd just like to take a couple of moments to discuss dark matter. This is by now a rather famous plot which shows you the sensitivity of present and prospective LHC. LHC on the way. Present and prospective direct searches for dark matter scattering. An interesting feature of this plot is this red dashed line here, which is the background from astrophysical neutrino sources. And the name of the game in dark matter experiments in the coming years will be to push the sensitivity down to this neutrino floor, and then, as a second stage, try to figure out some way of perhaps penetrating below the neutrino floor using, for example, directional information on the dark matter scattering. So this pink blob here marks the predictions of generic supersymmetric models. So we've analyzed this in some detail in the framework of those universal models that I mentioned earlier on, and our predictions are indeed within this general region of this red blob. If you go to more general supersymmetric models, the situation is somewhat different. In this case, you can get somewhat lower dark matter mass, but you can also get significantly lower dark matter scattering. So these models might actually provide a challenge for the next generation of dark matter detection experiments, and will highlight the need to find some way of penetrating below this neutrino floor. So direct searches for dark matter are not the only way to do this, and there's also been a lot of interest recently, and I'm going to hear about it in more detail later on in this meeting, about looking for dark matter directly at the LHC. And this is a comparison between the sensitivities of LHC experiments and direct dark matter searches in spin, in the case of spin-dependent dark matter interactions and spin-independent dark matter interactions. So what you see is that in the case of spin-independent interactions, the LHC is generally less sensitive than the direct searches, except for low mass. LHC has an advantage of low mass. Whereas if you talk about the spin-dependent interactions, you find that the LHC pretty much always has an advantage. So we'll be interested to see how this develops in the future. with the respective improvements in dark matter detection experiments and LHC searches. Now, it should be said that this comparison has ambiguities. Depends on the nature of the interaction, depends on the properties of the dark matter scenario. For example, if your interaction between dark matter and regular matter is mediated by some particle, what is the mass of that particle? And these are ambiguities that need to be taken into account when you're comparing LHC and direct dark matter search experiments. So the final topic which I would like to mention is what might be the future of Kaleido experiments after GLHC. So this is a very hot topic now within the Carter physics community, and one particular idea which is now being put forward is the idea for the next generation large circular collider. Actually, one should talk about it more as the circular collider complex for exploring the 10 TeV scale. So you could either put in photons into this large ring, in which case you could explore the 10 TeV scale directly, or you could put in electrons and positrons and do experiments with much higher precision than were done with that, or could be done even with the IRC. So in that way, you can explore the 10 TeV scale independently. So this is sort of artist's impression of how such a large circular collider might be located in the neighborhood of Geneva. Perhaps I should say how Geneva might be located inside such an accelerator. As you probably know, there's also somewhat similar ideas being discussed in China. So clearly such a facility would offer tremendous prospects for Higgs physics. This slide just shows you how the cross-sections grow as a function of the center of mass energy. Processes with multiple Higgs reactions, for example, have a much larger cross-section at such a machine. Alternatively, you could, as I said, put in electrons and positrons, and you would do high precision experiments. And on the left-hand side here, you see the prospects for precision electroweak measurements. So the little green bar here represents the prospective precision of such a circular plus-minus machine, which, as you can see, is far, far better than what was achieved with that, and which would offer you the prospect of testing from the supersymmetric scenarios, even if you can't see the supersymmetric particles directly. So that's precision electroweak physics, and this is a corresponding thing for precision Higgs physics. Here, the circular machine uncertainty is shown here as this little red error bar. One reason to show this slide is to highlight the fact that we theorists will have to do a lot more work if we're going to reach the full harvest of such a device. We have to reduce the uncertainties, the theoretical uncertainties, both in the precision electroweak processes and also in the Higgs model. So, just prepared one slide to talk about the prospects of dark matter. Maybe I'll skip directly to this slide here. We devoted a little bit of thought to thinking within the supersymmetric scenario, how heavy could dark matter particle be? And what we found is that the dark matter particle could weigh several TeV. And this would still be compatible with the LHC measurement of Higgs or the other supersymmetric constraints. So you might ask, well, if supersymmetric particles can be that heavy, what are the prospects for discovering at the LHC some future collider? So these various different color-coded lines here show you the prospects for discovering supersymmetry. And And you see that if you want to cover all of this supersymmetric parameter space, you would need a machine with 100 TB in the central mass. So, LAC-11 has produced a lot of theoretical confusion in high mortality rate amongst theories, unfortunately not amongst theorists. Perhaps the most interesting observation from LAC-11 has been the nearness of the top and then Higgs to the stability bound. String theorists, sorry, supersymmetrists may feel a little bit beleaguered, but as I say, I still think this is the best possible theory, and I take the point of view that supersymmetry anywhere is better than supersymmetry anywhere. I did hear a nice little quote from that well-known scientific philosopher Lionel Messi, who says, in particle theory, talent and elegance mean nothing without rigor and precision, which I interpret as meaning it's not enough to come up with brilliant, beyond the standard model scenarios, but you also have to do precise theoretical calculations so that you can actually test them. So, we've been working on particle physics now for a bit longer than a century. Many discoveries have been made. This plot here shows you the time lag between the proposals of new particles and their discovery. As is well known, the longest time lag so far has been for the Higgs boson. There was a time lapse of 48 years between the proposal and its discovery, which gave time for the Higgs to evolve. So, a final message to my supersymmetric friends. Supersymmetry, four-dimensional supersymmetric field theories were proposed just 41 years ago. So, compared with 48 years for the Higgs boson, we can still be a little bit patient. Thank you. That's what I...
So maybe I should start with some warning. By first reminding you that until a few years ago I was still building some X-less models, so maybe I'm not the right person to discuss actually X physics here. And I would like also to remind you that even distinguished physicists actually can advocate for the wrong direction. So for instance, if you look at a very important paper discussing for the first time the phenomenology of the Higgs boson, if you go to the conclusion, you will see that actually it's written that for this reason we don't want to encourage big experimental searches for the Higgs boson. Anyway, so we certainly all have a PhD, and it's true that for the first time in the history of physics, we have a consistent description of the fundamental constituent of matter and their interaction. And actually this description can really be extrapolated to very high energy, maybe as large as a Planck scale. But at the same time, we have another kind of PhD, namely a post-Higgs depression, because, we are not sure that we are going to discover anything else. And at the same time, all the big questions of the field remain widely open. We don't understand the hierarchy problem, we have no solution to the flavor problem, we don't understand the neutrino masses, and then we have no clue of what dark matter is made of, and we don't understand this asymmetry between matter and antimatter. So the real question is, of course, where and how does the standard model will break down, and which machine will actually reveal this breakdown. So even the string theorist actually has noticed that really Higgs discovery itself was a big discovery, and at the end the experiment worked better than expected, and the analysis uncovered a very difficult to find signal. So we can ask ourselves, why actually did it work better than expected? So certainly there has been a very hard work from the experimentalists. Maybe we have also been lucky with a positive fluctuation in the signal. At the end we are all doing quantum mechanics, so we have to rely on a little bit of a luck. And also I would like to point actually that this discovery was made possible thanks to the hard work from the theoretical community itself, who has computed more and more of this higher order radiative correction. And the effect of those radiative correction was actually to increase significantly the X cross-section production. So for instance, if you were to normalize all the cross-section at the leading order, so on the board level, let's say, the cross-section will have been actually far too small to allow for the discovery of the Higgs boson quickly. And thanks to those radiative correction that basically double or even multiply the cross-section by a factor 2.5, then certainly the Higgs discovery was in sight of the experimental end. So indeed, it's quite unlikely that Frank Petriello couldn't be with us today, and he sent me his slides yesterday, and I will try to cover part of his material, at least part of the slide that were about the Higgs boson. So we all know actually that the Higgs boson at the LHC can be produced in various different ways. The dominant way by large is actually by a fusion of gluon, the gluon being inside the proton. But there are also other possibilities, like for instance vector boson fusion, either with W or some Z's, or this associated production of a X with a W and a Z, the Ink-Schramm. And maybe potentially also for the future, we haven't observed this production mode yet, which is the production of the X in association with the pairs of quark and antiquark. So as I said, the dominant production mode is really the gluon fusion, and it took a long time actually to really perform all this computation, which now include really a lot of relative correction beyond the leading order diagrams. So the leading order diagrams is just this one contribution, since of course the gluon is a massless object, it cannot couple directly to the Higgs boson, but there is a quantum mechanical contribution due to the loop of the top quark. So here, on this little cartoon, actually, I've shown the timeline for the computation of this diagram. So the first computation, actually, that's from the 80s, and then the next to leading order computation, so one loop more than this leading order computation, was done about 20 years ago, and then nowadays we are actually at n-cube leading order. So the funny thing is that actually all this radiative correction now are automatically included in all these Monte Carlo tools, and basically they come at no human cost, right? You just need to press on the bottom and you get the result, and you can basically draw this kind of diagrams that show the production cross-section as a function of the Higgs mass. But of course these days we know more or less what the value of the Higgs mass is, so we can forget about all these diagrams and really focus on a particular line around 125 GeV. So now I would like to tell you a little bit more about this computation for the gluon fusion process. So as I said, the leading order is actually one loop diagrams that involve the top quark, and the best state of the art nowadays is actually n squared LO, so next to leading order, but this is actually computed in the infinite top mass limit. So instead of being a free loop diagrams, actually free loop process, you shrink this contact interaction between gluon and the Higgs to a point-like vertex, and then this n squared LO computation will be actually a two-loop computation performed at alpha s to the fourth. And what is the next frontier that people are actually working on? Well, it's two sides. Either they are trying actually to keep the mass of the top finite. In this case, n squared LO will really mean a free loop computation, still at alpha s to the fourth level. On the other hand, they are still also trying to do one loop more, but still in the infinite top mass limit, which is n cube LO. And there is a lot of activity these days really in performing this full computation in details. So that's for the inclusive cross-section. At the same time, you can also try to understand the different kinematic behavior of the production of the Higgs. So you would like, for instance, to look at the Higgs transverse momentum production. So clearly, at leading order, since you are producing only Higgs, the PT is equal to 0. But at next to leading order, for instance, you can also emit a jet, and then this will give a PT to the X. And surprisingly enough, actually, this is one of the only standard model computation which is actually known only to leading order. When you are at least trying to keep the mass of the top finite. People are also trying again to play some problem with the microphone. Good. Okay. So people are also trying to play the same game for the inclusive cross-section to take the infinite top mass limit, and then in this case I've been able to compute the PT distribution up to n squared LO order. And again, the frontier is actually either to compute this to n cube LO or to actually compute the first next to leading order computation while keeping the mass of the top finite. So overall, actually, the complexity of this computation is very similar to a computation that has been achieved very recently for the TT bar cross-section at n squared LO, and this is really a 2-to-2 process at 2 loops. So this is really what we are up to at the level of complexity these days in quantum field theory. So all the techniques are known. It still takes a long time actually to implement them into this kind of computation. So that was one slide of Franck actually that shows, the effect really of all this higher order radiative correction. So this is a leading order cross-section, including, some theoretical uncertainties due to the variation of the scale around the mass of the X. And then you see that by including the next to leading order correction, then you increase the cross-section by a factor 2. And also, what you can notice is that actually the theoretical uncertainty that has been estimated at leading order actually doesn't capture the next to leading order computation. So that was a little bit worrisome. Fortunately, things seems to converge now when you include the next to leading order correction, and now the theoretical uncertainty is well captured by the scale variation. And as I was saying, there is a lot of activity these days in computing things, this cross-section to n cubed LO, and this is the kind of diagrams that people have considered recently, and there have been a lot of progress along this line, but the final answer is still to come, even though now it's really inside, I will say. Another, as I was saying, another important direction is actually the computation of the PT spectrum of the X. And as I was mentioning, this is known for the moment only at leading order if you want to keep the mass of the top finite. If you want to send the mass of the top to infinity, then the PT spectrum nowadays is known to next to leading order, and this is really a big achievement since last year, basically, not next to leading order computation were known. Right? So this is certainly a big step forward. And you can wonder why should you be so interested in the PT spectrum. Actually, this has to do with the fact that we still don't know exactly the Higgs coupling to the top quark. And as I will mention later on, actually you can distinguish, the top running into the loop from the contribution of other particles that could also run into the loop by looking actually at the PT spectrum at very large PT. And I will come back to that at the end of the talk. Another thing that people are quite interested in on the QCD front is actually to do some jet veto. And then when you inquire, that you will produce the X in association with 1 jet, or 2 jet, and 3 jet, then it's becoming a huge business actually to estimate the theoretical uncertainties, because certainly, you need a prediction for the, let's say, for the cross-section, but you also want to know exactly what the theoretical uncertainty is. And there, people have noticed that you cannot play the same game as it is done in the inclusive cross-section when you vary the scale of the factorization and the renormalization scale around the mass of the X. If you do the same thing, this will not capture exactly the theoretical uncertainty when you impose some jet vetoes. So people are trying to develop actually some new methods to really estimate these theoretical uncertainties. And there is again a lot of work going on in this direction. So that was a lot of effort devoted actually to compute with more and more accuracy the signal, but there is another direction, which is actually computing also with higher accuracy the interference between the signal and the background. So naively, we think that for the X physics, this interference is very small simply because the X is a very narrow object, at least in the standard model. The ratio of the width over the mass is something like 10 to minus 5, so you will see that this interference will be very tiny. Nonetheless, there are some subtleties. For instance, in the gluon fusion production of the X, and then later on when the X decays into two photons, the signal is certainly a two-loop process, right? Because there is no contact interaction between the X and the gluon nor to the photon, so it has to proceed with some loop of, let's say, the top quark or the bottom quark, while the background actually can be generated at one loop. Right? You can have a one-loop process that converts two gluon into two photons. And this difference in the order of perturbation makes this interference larger than naively expected just by the ratio of the width divided by the mass. And actually, people in the late 80s have actually computed this interference and estimated that it could be as large as several 10% correction in the rate. But actually, when you're doing a more precise calculation, as those people did in the early 20s, there is actually some accidental cancellation, and the effect actually is brought down to a few percent effect. Nonetheless, there is some possible effect, in particular in the measurement of the mass of the X, or if you want, on the invariant mass of the two photons. And this shift, this interference has the effect to shift actually the invariant mass of the two photons away from the true value of the mass of the X. So this is certainly an effect that has to be taken into account when you want to measure the mass of the X in the two photon channel. And people have computed this effect is of the order of 100 MeV. And actually there is also a dependence on this mass shift as a function of the PT of the X. So basically, instead of comparing the mass of the X in the two photon channel versus the 2Z channel or the four lepton channel, you can simply rely on the two photon channel measuring this mass shift at different value of the XPT, and this will basically measure this with high accuracy, this interference effect. There is also some nice interference effect in another channel, which is the off-shell production of the X that then decays into 2Z with 4 leptons as a final decay product. And I will comment about that later because there is some interesting physics associated with this off-shell X production. Finally, I would like also to mention another interesting interference effect that people have considered very recently. Because in the previous example, if you want, the amplitude squared for the signal was always much larger than the interference effect between the signal and the background. But there are other examples actually where the signal itself is very tiny, and it's certainly much tinier than the interference between the signal and the background simply due to the very high background. So this means that in this case you can simply rely on the background to actually enhance the signal. Right? In the sense that you cannot see the signal squared, but you can see actually the interference between the signal and the background due to the large background. So that's a very nice example, right? Because it's really a way to use the background to dig out a signal that you're interested in. And one example that was proposed along this line is actually the production or the decays, for instance, the decays of the Higgs boson into a vector meson, for instance, a gypside plus a photon. So let's say at the signal level, there is this kind of diagrams, where, for instance, the Higgs will decay into a pair of charm quark, and then the charm will form this gypside. But if you compute the signal alone, this is far too small to be observed. On the other hand, this signal will interfere with this background, which is much larger, and then due to the interference, you will be actually sensitive now to the signal itself. And that's a way that has been actually proposed very recently to actually measure the Higgs coupling to the charm quark at the LHC. There is also other exclusive decays that have been considered, like Higgs decaying to a phi on a photon, Higgs decaying to a rho on a photon, or Higgs decaying to omega on a photon. And again, all these exclusive decays actually can give some interesting information about the possible coupling of the Higgs to light quarks on the leptons, light quarks in this case. So far so good for the standard model. So certainly, as again the string theory said, it was a big time in the history of physics, a great success, but at the same time the experimentalists haven't found what the theorists doing physics beyond the standard model told them that they will find in addition to the Higgs boson. There is not yet supersymmetry, no black hole, no extra dimension, nothing. So we can ask ourselves whether the theorists have been lying for so many years, or whether the experimentalists have been too naive to believe the theorists. So, as this famous Argentinian philosopher said, if you don't have the ball, you cannot score. Unfortunately now in Higgs physics, in physics, in high energy physics, we have the Higgs boson in our hands, and maybe the particle physicists can play as well as German against Brazilian. And I think it's fair to say that the Higgs discovery translates into a profound change in paradigm, namely from a missing standard model particle, now you can really use Higgs as a tool to explore the standard model and certainly venture into physics territory beyond the standard model. So there is still two approaches. The Higgs as a target itself, so you want to observe it in as many channels as possible to measure its properties. You want to check the coupling structure of the standard model and its possible deformation. And you want, if you observe any deformation, you want to interpret those deviations of the Higgs coupling as a sign of new physics and maybe learn something about the structure of physics beyond the standard model. On the other hand, you can also use the Higgs boson as a tool now that you have observed, that you know that it exists, you more or less know its properties, and you can use really the Higgs as a portal to new physics, either in initial state, for instance in rare decays, well, something that I already mentioned, when the Higgs decays in a strange way, in the exclusive way, in the Gibbs side with the photon, then you can basically use this rare decays to measure some deviation in the Higgs coupling to the light quarks. Or you can also search for flavor-relating Higgs decay, like Higgs decaying into a muon at tau, something that is forbidden a priori in the standard model, but can exist in any physics beyond the standard model for some reason that I will explain in a moment. But the Higgs could also be used in the final state as an object that can be reconstructed and tagged. For instance, the top can decay into a Higgs plus a charm, so again, a flavor-validating decays of the top quark in this case. Or you can even produce Higgs by the decays of an heavier Higgs. For instance, in 2 Higgs doublet model, like in supersymmetry, you have an heavier Higgs, and this heavier Higgs can actually decay into pairs of light Higgs. So basically, you can now look for this pair production of the Higgs and basically reconstruct this or the existence of this heavy Higgs. So that's a kind of example of physics that can be done with the Higgs boson in the initial or final state. So we have been discussed a lot about the Higgs physics, so maybe it's time now to remind you exactly a little bit in more details actually the properties of the Higgs boson in the standard model, keeping in mind actually any possible deviation from the standard model production. So Jordan already shows this very nice plot that reports the Higgs coupling versus the mass of the different particle, and the standard model prediction was that all this coupling should be aligned, right? And why is that? It's simply because in the standard model the Higgs plays an important role, which is the unitarization of all scattering amplitude. So if you take a massive gauge boson, you can put by hand the mass, but the problem is that with this description is that you end up with scattering amplitude that grows with the energy. So something that cannot be extrapolated at very high energy because it's not consistent with perturbative unitarity or the typical rules of quantum mechanics, right? So this means that you need new degrees of freedom to actually make sure that the scattering amplitude remains finite, and that's precisely the role of the Higgs boson. So you introduce the Higgs boson, the coupling of the Higgs boson to the longitudinal component of the W and the Z, written in a strange way here, but this is nothing else than the mass term for the W and the Z. So you introduce a linear coupling, and this linear coupling, in the exchange of the Higgs in WW scattering, certainly give an additional contribution, and this additional contribution also grows with the energy because you have some derivative interaction here, and this, the effect of this linear coupling, if you tune this parameter A to be exactly equal to 1 is such that the exchange of the Higgs boson precisely cancels the growth of WW scattering amplitude. And you can go further, for instance, for the W going into 2 fermion, you also have a growth of the cross-section unless you introduce the exchange of the Higgs boson with a coupling C which is tuned to be equal to 1 in order to restore perturbative unitarity at high energy. And even in double Higgs production by vector boson fusion, this coupling B here, the quadratic coupling between 2 Higgs boson and 2 gauge field, is equal to 1 in order for this amplitude to remain finite. And this is nothing else really than the property that I was saying, so A, B, and C are equal to 1 in the Standard Model, and the coupling of the Higgs are directly proportional to the mass of the gauge boson and the mass to the fermion. So basically this property, this linearity property, is nothing else than the requirement that the Higgs boson achieve its goal of unitarizing all the scattering amplitude and getting a series of massive particles which is consistent up to very high energy. So this is now the fit of the experimental data, and the experimental data seems in pretty good agreement with this requirement of this picture of the Standard Model. Nonetheless, we can ask ourselves whether such a fit is a consistent description. For instance, here you can see that you can still have very large deviation, for instance, of the Higgs coupling to the bottom quark. And you can ask, whether it doesn't it makes any sense to have this very large deviation and still keeping or including only the interactions that are predicted in the Standard Model. Most likely, if you find any theory that will generate 500% deviation in the bottom coupling to the Higgs, then at the same time, this new physics will also generate a new kind of interaction which have a different Lorentz structure than the one predicted in the Standard Model. And certainly when you are doing the fit, you have to include this time all this possible structure to have a consistent fit, which is not done in the fit that is reported here. Here, it was assumed directly that all the possible Higgs interactions have the same form as the one predicted in the Standard Model. So what I wanted to say is simply that if you want to do a good fit of the possible deviation of the Higgs coupling away from the Standard Model prediction, then you better need to rely on some tools like effective field theory, which is giving you a sense of when actually the fit that you are performing is theoretically consistent. Right? So there are still some missing information actually to complete the picture. So clearly here you have seen that the fit stops at the coupling to the tau, and clearly we would like also to understand whether this line continues toward the much lighter particle, like for instance the charm, the muon, or maybe the electron. It's fair to say that the LHC so far has no sensitivity to such a tiny coupling, because of course the coupling of the Higgs are proportional to the mass, so the lighter the particle, the smaller the coupling is. Nonetheless, there is already some interesting bond, for instance, of the Higgs coupling to the muon, which is telling you that clearly the Higgs coupling, to the different family of different generation of quark and the lepton are not universal. So the Higgs is totally different than the Z prime gauge boson. For instance, there is some coupling that differs from the different generation. And as I was mentioning, there is also the possibility later on at the LHC maybe to measure directly some coupling to the charm quark, either in the inclusive way, for instance by developing some charm tagging algorithm, or the exclusive way by measuring those rare decays, like Higgs going to Gibbs side to the photon. Then there is another also comment that I would like to make looking at this plot is actually concerning the coupling of the Higgs to the top quark. So as I was mentioning before, there is no, the LHC hasn't observed the associated production of the Higgs with a TT bar production, or with the TT bar pairs. So this means that actually the LHC hasn't been able to measure directly the Tokugawa coupling. You have only an indirect sensitivity via the loop processes, either in gluon fusion or in the decays into two photons. But when you are trying to extract the Tokugawa coupling from this loop, you have to make some assumption that basically the top is the only particle running into the loop, that there is no heavier particle. And actually, as a matter of fact, and I will give you some example later on, there is some model where at the same time you modify the top Yukawa coupling, but you also introduce some other particle into the loop, and the net effect will be exactly like in the standard model. So the total product, the inclusive production for the gluon-gluon fusion into X will be exactly the one in the standard model. Still, you have new physics, that actually enter into this process. So saying in another way, when you are looking at the inclusive cross-section, you cannot really disentangle the structure of the loop, and you can totally miss some possible new physics effect. So that's why it's important to go at some point beyond inclusive quantity if you want to have access to this top Yukawa coupling. And as John was mentioning, this is a very important physical parameter. For instance, it really controls the fate of the electric vacuum. So you would like to know, in a model-independent way, what the value of this coupling is, right, without making any assumption. So another important properties of the X in the standard model is that it doesn't mediate any flavor-changing neutral current. And this is due to the fact that in the standard model, the Yukawa interaction are the only source of the fermion masses. So you have this dimension 4 Yukawa interaction, and when you expand around the vacuum, you generate the mass for the fermion, and you also generate a linear interaction between the X and two fermion. But the fact that you start with only one type of interaction is telling you that those two quantities, the mass matrices and the matrix of the X fermion interaction, are proportional to each other, namely that they can be simultaneously diagonalized. And as a result, there is no FCNC that can be mediated by the X boson. But of course, this is not necessarily true, in any model beyond the standard model. So for instance, if you have more than these four-dimensional Yukawa interactions, so for instance, if you add on top of this a dimension 6 Yukawa interaction with extra power of the X field, then you get two different matrices for the mass and the Yukawa interaction. And in this case, you cannot simultaneously diagonalize those two matrices, and then you will generate some X-mediated FCNC. This is also the case actually when the standard model quarks on lepton mixed with some vector-like fermion that can get a mass by themselves because they are vector-like objects. And in this case, you will also generate X-mediated FCNC because you have another source of the mass for the standard model quarks on the lepton. So that's why it's so important actually to search for flavor-violating X decays, because you are really, by trying to observe these quantities, these particular decays that are forbidden in the standard model, then you can really learn about the origin of the masses of the quark on the lepton in great details. So as John was already mentioning, for instance, you can, there is only very weak, actually, indirect constraint on these possible decays. For instance, in EDMs or muon decay into an electron and a photon was constraining only the branching ratio to be below 10%. And it's only Atlas and CMS that have a sensitivity below this indirect constraint, something around 1%. And certainly some precise machine like the linear collider or this future circular collider with electron and positron can certainly do a better job and bring this bound to a sub-% level. So I wanted to show some analysis that have been done recently along this line by the CMS collaboration that have looked actually into the X decays into tau and muon, and they reported actually some possible excess compared to the expectation. And the funny thing is that the LHE now X data is actually competitive, and it's actually better than indirect constraint like the tau decaying into free muon, the tau decaying into a muon on a photon. The LHE are 1 or 2 order of magnitude better than this indirect bound. And the other comment is actually the LHE now is entering the region of parameter space that are theoretically interesting, where you expect actually this branching ratio to have a size which is related to the mass of the tau on the muon. So namely, the theoretically interesting region should be below this diagonal line, and here you see that actually the LHE is really probing this region. So that's certainly something that we should keep an eye on, in particular to understand whether this anomaly will go away and whether you can improve entering better in this region, and certainly machine like ALC can prove a 30% brushing ratio for this flavor validating decays. So now I would like to comment a little bit about precision X physics in physics beyond the standard model. So we'll make the assumption, as it seems to appear from the experimental data, that there is actually a mass gap between the width scale and the scale of new physics. And in this case, I will integrate out any possible new physics and try to describe everything in terms of an effective field theory using the standard model degrees of freedom. So this means that in addition to the standard model Lagrangian, you will start writing some higher dimensional operators, so operators of dimension 6, dimension 8, etc. And those operators clearly should respect the symmetries of the standard model, at least the gauge symmetry, and maybe also partly the global symmetry, the accidental global symmetry of the standard model. So now the question is actually what kind of information X physics has brought into the exploration of this deformation of the standard model. And actually, it was realized rather recently that some of the deformation, so some of these operators of dimension 6, were not probed or were totally unconstrained before the observation of the Higgs boson itself. So for instance, you can take this dimension 6 operator, you have the gluon field strength, which is an operator of dimension 4, and then you add 2 power of the Higgs field. So this makes an operator of dimension 6. So now, if you are in the vacuum, so if you are not able to produce the Higgs boson, you can simply replace this operator of dimension 6 by expanding the Higgs around its vacuum expectation value, and the effect of this dimension 6 operator will be simply to correct actually the kinetic term of the gluon. So this means that it simply amounts to a redefinition of the input parameter for G strong. So this means that there is no way actually to see the effect of this operator in the vacuum, because it's just a simple redefinition of the input parameter, something that is unphysical clearly. So this means that if you want to see the effect of this operator, then you certainly need to have Higgs boson excitation itself. So you need Higgs in the initial or final state in order to probe this dimension 6 operator. And indeed, this operator has clearly some important effect in the gluon fusion production of the Higgs, 2 photons producing the Higgs boson, and then this operator has a huge effect comparable to the loop of the top quark. So you can play the same game and try to come up with a list of those operators that were not probed at all in the vacuum. So some of the operators that needed the Higgs to be tested, and how many are there? Well, there are as many as the number of input parameters in the standard model, and if I restrict myself to one family of quark and leptons, the number is only 8. There is G strong, G SU2, G of the U1 of hypercharge. There is the mass of the W, which is also related to the mass of the Z in the standard model as a consequence of the custodial symmetry. There is the mass of the Higgs boson itself, and there are the mass of the free type of fermions, the top quark, the bottom quark, and the tau lepton. So this makes 8 input parameters, and this means that there is 8 operators of dimension 6 that were not constrained at all in the vacuum, and these are the operators that can be tested once you're able to produce the Higgs boson. So out of those 8 operators, 6 have been measured quite well recently, with the caveat that we are not able again to disentangle the top Yukawa from the contact interaction to gluon, but I will come back into a moment about that. And out of these 8, 2 of them are still to be measured at the LHE. The one which controls actually the Higgs coupling to the Z and the photon, and that's an important search which is going on at the moment by Atlas and CMS. The decays of the Higgs into a Z and a photon is something that hasn't reached the sensitivity of the standard model yet. It's something like 10 times the standard model cross-section, but still it starts being probed. And then the other important channel is actually the multi-Higgs production. Like for instance, blue goes to 2 Higgs boson, that will be actually giving the first indication of this Higgs self-coupling that is controlled by this dimension 6 operator. So there is almost a one-to-one correspondence between those dimension 6 operator and the famous kappa parameter that were introduced by the experimentalists that were just some deformation or some rescaling of the Higgs coupling compared to the standard model. There is a little bit of subtleties in the correspondence between the two. So for instance, in order for the experimentalists to perform this feat, they need to make some assumption about the Higgs width, whether the total width is just the sum of the partial width into a standard model object, or whether there is new additional or undetected or invisible decay mode of the Higgs. While clearly in this effective field theory approach, the width approximation is really built in, and there is no other possible contribution to the Higgs width. Then the experimentalists were also trying to measure separately the coupling of the Higgs to the Z boson and to the W, claiming that it's a probe of the custodial symmetry in the standard model. It's true, except that this custodial symmetry were already tested or probed indirectly in the vacuum, either by looking at delta rho parameter or by looking at the anomalous triple gauge coupling. This way, in such a way that actually there is no hope to be sensitive in the Higgs data into some possible violation of the custodial symmetry. So what I want to say is simply that the experimentalists were, in a sense, wasting their time in trying to measure two independent quantities where we already have some strong interaction that those two quantities were correlated to each other. And the last remark that I wanted to make is that actually in this feat, they have introduced the Higgs coupling to the gluon and to the photon, but they haven't separated the UV from the infrared contribution to this coupling in such a way that they cannot distinguish whether there is new particle running into the loop or whether this coupling is just due to a modification of the top Yukawa coupling. And again, from the theoretical point of view, it's important to know the origin of this contact interaction to gluon and photon, whether there are new particles into the loop or not. So I was saying that actually there is no way to constrain those dimension 6 operators, this 8-dimension 6 operator, in the vacuum. This is actually not totally true, because there is indirect way, for instance, using electric precision data. So if you take this modified, this dimension 6 operator that modified the coupling of the Higgs to the W and the Z, actually this operator will give an indirect contribution to the self-energy of the W and the Z at one loop, simply because here, at one loop in the standard model, you have the exchange of the pion and you have the exchange of the Higgs boson, and the two diagrams actually have a cancellation between each other due to the particular value of the Higgs coupling to the gauge boson. So now if you have this dimension 6 operator, you will modify this coupling, and this cancellation doesn't occur anymore. So this means that if you have this dimension 6 operator, you will be left with the logarithmic divergences in S and T, or epsilon 1 and epsilon 3. So clearly you can use the lab data to constrain those possible contributions due to modify Higgs coupling to the W and the Z. And that was what down here. So in this ellipse, in this ellipsis, it was just the fit of the Higgs data themselves, and now you can add the fit to the electric precision data from lab, and then you see clearly that the ellipses shrink and reduce the possible deviation of the Higgs coupling to the W. But of course, this is totally indirect, and in addition to this additional contribution due to the modified coupling, you could also have additional UV contribution that for some reason cancel each other, and then leave with a modified coupling and still have another contribution to S and T. Okay. Went into the details here, it's maybe a little bit too technical. So in the description that I gave so far, I was making the assumption that all the Higgs coupling actually respect the CP symmetry. But this is certainly something that you would like to test, in particular, in view of the importance of the CP violation, for instance, for generating the asymmetry between matter and antimatter. So clearly in the standard model, there are two sources of CP violation. There is one, which is simply the phase of the CKM matrix. This is a large violation of the CP symmetry, but actually the physical effect of this large phase is actually screened by the small value of the quark mass. as a net effect, actually, this phase doesn't play any role in electric baryogenesis, or actually it's not large enough to generate this larger symmetry. The other source of CP violation is the standard model is theta QCD, and as far as we know, this parameter is very small, but we don't really understand why. We have a nice mechanism to explain why it's small, like for instance the axion, but we still don't know whether it's a true mechanism that is being realized in nature now. So the question was whether the X coupling, the X being a CP even object, can violate CP also. And again, you can play the same game as I was doing before, trying to write an effective Lagrangian to capture the deformation of the standard model. And you can count again the number of parameters and the number of deformations that were not probed in the vacuum, so the number of deformations where you needed the X boson to put some constraint on those deformations. And actually it turns out that in this case, in the CP violating sectors, there is 6 of these deformations. There are 3 of them that control the coupling of the X to the fermion, and then there are 3 of them that control the coupling of the X to the gluon, to the photon, and the photon on the Z. So in principle, again, those 6 parameters were totally free before actually observing the X boson. As before, actually there is also some indirect constraints that were controlling the size of this possible deformation. So for instance, if you have a violation of a coupling of the X to the photon that violates CP, you can then close a loop. So you have a CP violating interaction here between the X and the photon. You can close a loop and generate an electron or quark EDM at one loop. And clearly there is strong bond on such EDM in such a way that you can get indirectly some strong constraint on this CP violating coupling of the X to 2 photons. And if you put the numbers, it will tell you simply that this kind of interaction here has to be smaller than 10 to minus 4. Or if you want to translate it in terms of a scale, it means that the scale that controls the CP violating operators has to be above 25 TeV. So this means also that it's very hard to believe that LHE will see any CP violating effect in the X coupling to the photon, simply because you will need a sensitivity in theory to measure some coupling which are below per mil, 0.1 per mil. So this means that it's quite unrealistic to search for this CP violation in the X coupling to photon. Of course, this is an indirect measurement, and there is always some assumption. So for instance, if you have noticed that in computing this EDM, you need to know the X coupling to the electron or to the light quark. Here I assume, when deriving this bond, I have assumed, or those people have assumed, that this coupling takes the same value as in the standard model, but a priori this is something which is not measured, and it could well be actually that the X coupling to the electron is actually vanishing, in which case there is not such a contribution anymore. But that's the price to pay, if you really want to be able to see any CP violation effect in the X coupling at the LHE. What about the X coupling to the top? Whether or not they can mediate CP violation, they can include some CP violation. Again, you can play the same game, and this time you can actually draw a 2-loop diagrams that contribute to the EDM of the electron. And this is telling you that the X coupling, X CP violating coupling to the top has to be below 1%. So again, something which will be very hard to observe at the LHE, provided actually that those coupling of the X to the electron remains the same as in the standard model. So maybe if you still want to observe some CP violation in the X sectors, one possibility would be actually to look at CP violating coupling to the tau. This is in theory not indirectly constrained by this EDM measurements. So what should be the priorities in X physics for the next few years? So certainly, I think the number one priority should be a better measurement of all this deformation of the standard model that were not tested elsewhere than in X physics. So you can do it by improving the inclusive measurement, or also by start looking at differential distribution. And then, after measuring with enough precision these 8 primaries directions that are sensitive to physics beyond the standard model, you will also like to measure all the other possible X coupling that have already been tested indirectly, either by electric precision measurement or by anomalous triple gauge coupling. In the sense, what you are really interested in is to test the structure of the standard model coupling. So in the sense, you have, in the standard model, you have vertices without X boson, vertices with one X boson, vertices with two X boson. And certainly there are some symmetry or some correlation that exists between those various vertices. Right? For instance, when I was drawing this very nice plot, this linear rigid plot that shows the linearity of the coupling of the X to the mass of the particle, what I was doing is actually testing this correlation between 0 X vertices, namely the mass of the particle, and 1 X vertices. But there is also kind of correlation that you would like to test. For instance, the structure of those interactions that follows from custodial symmetry. You would like to see whether or not this structure follows when the X is turned on. The real question actually, and I think this is not something that is done yet, and not known yet, is actually what is the position in X physics that you need to actually be able to test those correlations. So for instance, you know that electric precision data is known to the per mil level, so this means that certainly you also need to measure at the per mil level the X coupling. And that's something that will be very hard to do at the LHE, clearly, because the limited precision will be at most of the order 5% or 1% at very high luminosity, but certainly you won't go below 1%. So this means that the correlation with electric precision data will be very hard to establish. But there is also other sort of correlation between, for instance, single X production and double X production that you would like to probe whether or not those correlation follows in the experimental data. And that's one thing that you can do, for instance, indeed trying to compare double X production with single X production. And this, again, is relating basically the single X coupling to coupling that involve more than one X boson. So as I was mentioning before, if you want to maintain perturbative unitarity in WW goes to two X boson, so double X production by vector boson fusion, you need a correlation between this quadratic coupling and the linear coupling. So far, the linear coupling starts to be constrained by LHE data, but LHE at the moment cannot tell anything about this quadratic coupling because we haven't been able to observe double X production yet. So what you can notice is that if X is really part of an electric doublet, then there is a correlation between those two couplings. Right? So the linear coupling is related to the quadratic coupling in this way. And actually, the deviation away from the standard model, so I remind you that in the standard model, A is equal to B is equal to 1. So any deviation away from the standard model is actually controlled by a single dimension 6 operator, which is this one. This means that you have a relation between the deviation of B and the relation of A. And so there is a universal relation that due to the fact that you have a single operator that controls those deviations. And the deviation away from this universal relation is actually controlled by, for instance, operator of dimension A. So the first thing will be, for instance, at the LHE to measure separately the deviation of the linear coupling, the deviation of the quadratic coupling, check whether or not this universal relation holds. That will be a probe whether or not the X is part of an electric doublet. So namely, we will learn actually the quantum numbers of the X outside the vacuum, right, which is an important quantity. Everybody assumes that it's part of an electric doublet, but this so far hasn't been really established. Right? So that's part of the program that I outlined here to really prove that X is part of a doublet. And then, if you have enough sensitivity, maybe you can also try to be sensitive to the deviation away from this universal relation. So that will be a way, for instance, to test the deformation of the standard model at the dimension 8 level, and this can bring some valuable information, for instance, whether or not the X is actually a Goldstone boson, a pseudo-Goldstone boson. In this case, you can actually compute explicitly those deviations away from the universal relation, and then by measuring them, you will be able to see whether or not the X is a pseudo-Goldstone boson or not. So that depends, of course, a little bit about the precision and the size of those deviations. So for instance, if you have deviation of the order of 10% with a precision of 1% in the measurement, this means that you are really able to actually probe, or first of all, establish this universal relation, and then probe the possible deviation from this universal relation. So in this case, you can prove whether or not the X is a ghost one or not. If the deviation are of the order of 1% with a precision of 1%, then the only thing that you can hope to establish is whether or not the X is a doublet, but you have no way to tell whether the X is a ghost boson or not. Okay, so far so good about the description really of, let's say, single X processes with a little bit of incursion into double X production. But now I would like to discuss actually some more kinematical distribution of the X boson. Let's say when the X is produced with a large transverse momentum, or when the X is produced actually off-shell. So why going beyond actually inclusive X processes? So far the LHE, the X has been produced mostly on-shell in processes with a characteristic scale which is close to the mass of the X boson. So what I want to say is that all the processes that produce the X are actually dominating by threshold physics. So this means that you have access to the X coupling at a scale around the mass of the X boson. But of course, this is not really what you would like to know, right? For instance, the deep properties of the X was actually to restore perturbative unitarity, which is a property of the X coupling at very high energy. So you would like to have access to the value of the X coupling at energy as large as possible. So this means that in this case, you have to go away from the inclusive cross-section, and you need to look, for instance, at the PT distribution or off-shell production, where clearly the X is produced with an energy which is much higher than its mass. And in a sense, it's a program very similar to what was done between LEP 1 and LEP 2. So at LEP 1, you were producing the Z on-shell, and this was giving you some nice constraint on this oblique parameter S and T. And then off-shell at LEP 2, with more energy, you were actually probing some other orbit correction like W and Y that was a way actually to parameterize four Fermi interaction in universal theory. Right? So clearly, by going off-shell, you are being able to put some constraint on additional deformation away from the standard model. So that's a game that we would like now to play also in the X physics. And one important application to this, to study this kinematical distribution is indeed something that I was alluding to before, to be able to disentangle the top Yukawa coupling from additional possible contribution to the loop diagrams. So I was saying already before that the inclusive cross-section is actually unable to resolve the top loop, and that's something you can understand very clearly. For instance, if you look at the inclusive cross-section with the top mass finite at 173 GeV and the top mass which is 10 to infinity, then you get only a 1% correction to the total inclusive cross-section. So this means that the inclusive cross-section doesn't see the finite value of the top mass. You don't see exactly what is going on into the loop. Right? So if you want to measure individually the top Yukawa coupling, or the interaction between the X and two top, what you need to do is actually to have access to a process that probes this interaction at tree level, and clearly the channel to look at is TTH, right? The production of the X in association with the pairs of top quark. But this is notoriously difficult due to the difficult finite state, the fact that the top decays, so you have many particles in the finite state, etc., that you cannot really reconstruct. And at the end of the day, even at very high luminosity LHE, you won't get a very high precision in the measurement of this coupling, something like 10% or maybe 5%. Even at the linear collider, the precision won't be fantastic. It will be something like 10% compared to other coupling that can be measured 1% at the linear collider. So clearly here, there is a need to come with an alternative way to actually measure the top Yukawa coupling. And one way to do that is actually to look at some kinematical distribution, in particular at the PT, the transverse momentum of the X boson. So the inclusive cross-section is certainly dominated at threshold, so there are very few events with the large PTs of the X, but those events actually are very sensitive to the value of the top quark. So for instance, this is everything which is normalized to the infinite top mass limit, and here you see that the effect at a PT of the order of 300 GeV is of the order of 30%, so then compared to the 1% in the inclusive cross-section. So clearly, looking at the cross-section with a cut on the PT of the X of the order 300 GV can give you a very good sensitivity now on the detail for what is going on into the loop. Of course, the price to pay is, of course, that you are losing a lot of event. So for instance, the inclusive cross-section is of the order of 2000 femtobarn, and if you require a PT of the X of the order of 600 GV, then you are losing 3 orders of magnitude in the cross-section. But still, this cross-section with very few events actually contain more information than the inclusive cross-section.